Welcome to the Rory Academy YouTube channel. We share valuable information about power electronics technology and its emerging applications. Ever wondered how your phone, laptop, or even solar panels work? It's all thanks to tiny charge carriers, electrons, and holes. Let's break it down in the simplest way possible. Today we discuss about electrons and holes. A silicon atom has 14 protons, neutrons, and electrons. It has 2 electrons in the first shell, 8 in the second, and 4 valence electrons, allowing it to form covalent bonds and create a tetrahedral structure with 4 neighboring atoms. In summary, a silicon atom has an atomic number of 14. Its electron configuration fills the p orbital first, followed by the 3s orbital with 2 electrons, and then the remaining 2 electrons occupy the 3p orbital. There are 4 valence electrons in the outermost shell. Silicon has a diamond cubic crystal structure with a lattice parameter of 0.543 nanometers. The atomic number of silicon on the periodic table is 14, indicating it has 14 protons and 14 electrons. Hence, the electron configuration for silicon can be obtained as 1s squared 2s caret 2p caret 6 3s squared 3p squared. The s orbital, which is represented by s in the above configuration, can hold 2 electrons, while the p orbital can hold up to 6 electrons, and the d orbital can hold up to 10 electrons. Let's break down the electron configuration for silicon. We have the 1s orbital, which will hold 2 electrons, the 2s orbital, which will also hold 2 electrons, and the 2p orbital, which will hold 6 electrons. Then the 3s orbital will also hold 2 electrons, and the final 3p orbital holds the remaining 2 electrons. This is the electron configuration. A silicon atom has 14 electrons, with 4 being valence electrons in the outer shell. When silicon forms a single crystal, it can be used for semiconductor products. During crystallization, the atoms share electrons, resulting in 8 electrons around each nucleus. Pure monocrystalline silicon does not conduct electricity well, but doping it with impurities enhances its conductivity. Semiconductors are classified as p-type or n-type based on the impurities used, and these junctions are combined in a single chip to create electronic components. By doping pure silicon with group 5 elements such as phosphorus, with 5 valence electrons in its outmost shell, extra valence electrons are added that become unbounded from individual atoms and allow the compound to be an electrically conductive n-type semiconductor. This electron is extra in this structure. This is a free electron. When voltage is applied, it changes to a state where the electron is drawn to the positive plus symbol and can move freely. Boron serves as a p-type dopant and possesses only 3 electrons in its outermost valence shell. When boron is introduced into a silicon crystal lattice, a single boron atom can form bonds with 4 neighboring silicon atoms. However, due to its limited number of available electrons, specifically just 3 for bonding, a vacancy is left in the otherwise stable structure of the silicon. This absence of an electron creates a hole, which can be thought of as a missing piece in the electronic framework. Essentially, this hole represents not just a lack of charge but functions as a virtual particle, symbolizing a space where an electron would normally reside, contributing to the overall behavior of the semiconductor material. Electrons are drawn to the positive pole and move to close holes. Then, as the electrons move to vacant holes, new holes are created, and then the adjacent electrons move to the new vacant holes again. As this process is repeated, electrons move toward the positive pole, and at the same time, the holes appear to move toward the negative pole. Only electrons are actually moving, but the holes can be considered as having positively charged particles. Remember to like, subscribe, and hit the notification bell. Thanks for your support.